a brief of existing scheme, which I already had presented in the previous slide. Just it's a bit graphical so that you can easily understand that the natural gas and condensate is collected in 15 area. Condensate is knocked out and was being sent to oily sewer, and then the oil from the oily sewer it's get collected in the basin, that is S1203, where it is separated on the basis of density difference. Oil comes to the top because of lower density. Water and the sand stays at the bottom. So this water and sand is then sent to equalization basin. Equalization basin is basically just a small basin in which this water along with other condensate gets mixed and gets a settling time, so that all the water gets a homogeneous analysis. And then this is sent to a rainwater sump, that is S5201, which is from there it is pumped to either SCARP or EP based on the analysis. S5201 is gravity settling basin, and S1204, as I already mentioned, that is just to dampen the variation of flow rates and concentration coming from various streams of the plant. And also S5201 is just a pit, and which is provided with a submersible pump for either shifting fluid to the SCARP or the drain. Diversion of total waste to EP is not desirable and becomes problematic, especially in view of high level during winter and rainy seasons. To mitigate this problem, we opted for a cheaper solution because these problems were not frequent. They were only experienced once the condensate is coming from a high amount of condensate is coming with the gas, and that we come to know when once during routine visits to the 15 area knockout vessels, which are provided with the high level alarms as well as normal GLGs, so that whenever the condensate is present in the knockout, we can drain it. So the proposed solution was just to provide an atmospheric tank to separate the oil from condensate before being disposed of into chemical sieve. Condensate drain from all knockouts will be collected into new tank. This tank will be isolated after condensate drainage from knockout to provide residence time for oil separation. As we know that oil is lighter in weight, it settles at the top, and it goes at the top, and the condensate remains at the bottom. So condensate removed from the tank will be sent to the chemical sewer, and oil will be discarded to existing oily sewer system. There are various sewer systems being operated at the plant depending upon the effluent they are carrying. Chemical sewer is a sewer in which different chemicals which need to be processed or either can't be processed are collected, and they are mandated to be sent to evaporation ponds. The other sewer is the oily sewer, in which I have already told that the oily sewer is sent to S1204, where it is separated from the condensate, and the oil is sent to is collected, and the condensate is sent to SCARP or either EP. This tank is designed to handle a capacity of 5,000 liters because we have been experienced that condensate quantity in any particular shift remains within 1,000 to 2,000 liters. So the maximum condensate per day would be less than 5,000. So provide an ample amount of volume, or to avoid future contingency as well. Once the wellhead pressure keeps on declining and the condensate quantity keeps on increasing, we have a significant capacity margin in the new tank, so that those capacities can also be retained. An overflow line is also being provided and will be routed towards oily sewer via open channel. So this tank will be provided with a breather for venting any absorbed gas to avoid overpressurization of the tank. A full range side GLG will be provided. As I've told you that this tank would serve as a middle storage, intermediate storage. So we didn't provide it with any exceptional level control mechanism. So a full range side glass to be provided on the tank to observe the level and separated layers of condensate and oil. An inspection window is provided at the top of the tank for observation and measuring the level with its rod if required. Condensate removed from the tank will be sent to chemical sewer, and oil will be discarded to existing oil sewer through an open channel. An underground piping of 6-inch will be laid from area 15 to nearby chemical sewer. This was the drawing for this tank. which with these dimensions, that dia would be 2.5 meter, and elevation would be around 1 meter, provided with a breather and with the inlet and outlet nozzles. This will be the side glass. This nozzle 3N would be used as an outlet nozzle for the oil and the condensate. So this would be the new proposed scheme, where from 15 area, this would be sent to tank, with where there would be gravity settling. Oil resides at the top and sent to oily seaver, and condensate at the bottom sent to the chemical seaver. This is the PNID. This is the work that normally chemical engineers or the design modification requires. That what would be the, sorry. I hope you can all see the PNID again.
Yes.
Okay.
Yes, we can see.
Okay, thank you. This is the knockout drum, that knockout vessel that is available at the inlet of 15 area, in which natural gas comes into enters from the top, and the condensate is collected at the bottom. This condensate is then sent, was being sent to oily seaver, but this is no longer the arrangement. This is being now diverted towards the new tank, from where it settles. We provide the settling time, and the condensate from the bottom is sent to to the chemical seaver, while the oil is sent to S-pipette, that is called the oily seaver, and is being handled in 12 area as previously. Also, other knockouts in this area, which are for the fuel header or the feed header, are also provided with the same arrangement, that any condensate from these knockouts will also be collected in the same tank, and they would be provided with the residence time for settling. I was discussing the requirement of the hazard study. In these studies, we try to identify any unforeseen hazard. We try to identify some unforeseen hazards that might be happening in case we had not done the study properly. So in case of this tank, there were, you can say, deviations selected in case of high level, high pressure, flow, and temperature. In case of high level, the cause would be human error, because the valve or the feed to the this tank is being operated with a manual valve, which would be done by an area operator. So consequences would be that the tank may overflow or overpressurization of this tank. The safeguard is the overflow line is provided with respect to the oil or condensate overflow, and that is directly connected to the existing system. So in case of overflow, the oil or the condensate would be going to the sewers. Side glass is available on the tank as well, and the breather is provided to avoid the overpressurization. Similarly, low tank level, that also could be caused by human error. Natural gas breakthrough in the CY channel, that is chemical sewer. So breather is available.
Sorry to interrupt. The table, the hazard analysis table is not being displayed right now. It is showing process has, yes, it's not being displayed.
Okay. Is it clear now?
Yes, yes. Please continue.
Okay. Sorry. Okay. For the low tank levels, we also have the breather is available to prevent any gas breakthrough in the CY system. In case of pressure, as I was told, that this tank is provided with is at ambient pressure conditions. So any gas breakthrough from the natural gas system would lead to damage and of the associated piping if had not been provided with a breather. So we have catered for the breathing system as well, the vent system as well in case of overpressurization. That would only be caused once the operator opens the valve too much, and the liquid, along with liquid, the gas breakthrough from natural gas breakthroughs into the system, into this tank. Similarly, low pressure tank can only happen if the tank is closed and and the vacuum is created inside the tank due to condensation of the carry forward gas condensate, or for that reason also breather is available so that air can be taken in. Flow, with respect to flow, overflow lines provided to mitigate the contingency of high inflow, and with low flow there is no such hazard associated, so no safeguard is available. Temperature is not the issue in any case because the condensate travel at ambient conditions, so we don't have any hazard associated with high temperature. I hope the slide has changed again. Okay, then the economics. This project was estimated based on the installation of the tank. This is the economics that the way we carry it out. That number of valves that would be required, along with their pressure rating and their costs. Piping along with their length and the piping spec. The piping spec defines the material and the thickness of the piping and of the fittings on the piping. So that piping spec is very important in that regard. The cost numbers are derived based on the procurement that we carry out normally at our plant for different modifications. So we have a pool of cost estimates already available with us with the latest, you can say, procurements. So we use that data to get the, you can say, piping cost estimates or equipment estimates. If we don't have that available in our record, we ask for the vendors put reports to get that cost estimate done. So this would be the, you can say, just had an idea. You can have an idea that different materials which we expect for the modification are enlisted and their costs are tabulated. Based on the scope of the job, then its fabrication and installation costs are estimated. It's a rule of thumb that if you are just going to do some equipment or you can say welding or installation thing, then around 20% of the cost estimate, actual cost is estimated as installation and fabrication cost. So the total cost was estimated to be 4.8 million for this project. Moreover, in order to reduce the cost, we had already redundant oil of old 5-water network, which was also of 6-inch dia that was used as underground line to chemical sewer. Utilization of old pipe reduced this cost by 50%. So this project was executed, you can say, initially it was estimated to be completing 4.8 million, but because of reduced piping cost, that is, you can say around 2 million costed, the main chunk was this one. So with the reduced cost, we were able to save 2 million from that, and the whole project was completed in 2.8 million. So this was a brief introduction of this improvement that we carried out on our plant. And this concludes presentation from my side.